Good morning. Today I'm going to take you through another subset of subtopics under solving system of linear equations, which is the LU decomposition methods. And under that we are going to discuss the Doolittle method, the Kraut method, and the Kolesky decomposition method. So these are the three subtopics under the LU decompositions that we are going to discuss. What is LU decomposition? We are trying to solve the system of linear equations that we are familiar with. This time, trying to pass through another way to get it done. What this is all about is assuming we have a system that looks like this. 2x1 is equal to 8. Then x1 plus 3x2 is equal to, let's say, let me use 13. Then x1 plus x2 plus x3 is equal to let's see, 8, or let me use 12. With this particular system, everyone agrees with me that solving the system is very easy. Why is it easy? It is easier because I can just solve by the way of forward substitution, where from the first equation, I can easily just solve for my x1, which is going to give me 8/2. I put, that gives me 4. I put my 4 here, and the second answer will give me 4 plus 3x2 is equal to 13. And that's when I subtract and find my x2, my x2 gives me 3. Then when I substitute all of them, I'm going to get my x3. X3 come out as this plus that 7, so subtracted from that, x3 come out as 5. So you see that it is very easy to solve a system that looks like this. And what kind of system is this? This is a system where the coefficient matrix looks like 2, 0, 0, 1, 3, 0, 1, 1, 1. What kind of matrix is this? x1, x2, x3 is equal to 8, 13, 12. What kind of matrix is this particular coefficient matrix? This is a typical matrix, a typical lower triangular matrix. Lower triangular matrix. This matrix has a unique feature. It is just a lower triangular. So it tells us that if our system is such that the coefficient matrix is a lower triangular matrix, then solving the system is very easy. In the same way, if you had a system that looks like this, let's say x1 plus x2 plus x3 is equal to 15. Then 2x1 plus x3 is equal to, let's assume, maybe 11. And then x3 is equal to, let me use 2x3 is equal to 6. Assuming we have this system also has some similarities with the very first system I solved, because this is a system that can be solved easily by starting from the bottom up. This time we call it back substitution. You find your x3 from the last row or the last equation, that gives us 6 on 2, that gives us 3. And then you put your 3 there, you get 2x is equal to 11 minus 3, so 2x2 is equal to 11 minus 3, which gives us 8. Then my x2 is equal to 4. And then when I substitute all these two things there, I get my x1 to be equal to 8. So you see, these kind of systems are very easy to solve. And what kind of system is this? This is a system that can be put in the form 1, 1, 1, 0, 2, 1, 0, 0, 2. This x1, x2, x3 is equal to 15, 11, 6. This is a system where the coefficient matrix can be described as what? Upper triangular matrix. A triangular matrix. And this kind of system is also easy to solve, just as the lower triangular matrix. So mathematicians realize that instead of solving a square matrix, or a square matrix that is neither lower nor upper triangular, then it is, if we can find a way of converting any square matrix A into two parts, such that one is a lower triangular matrix, just like the top one that we discussed, and the other is an upper triangular matrix, and the product of the two gives us the A. Then we are likely to solve a system that looks like this, as well as a system that looks like this, which are both easy to solve. So the coming in of the method called LU decomposition. So this method, all that it entails is that you want to decompose the matrix A into two parts, such that one part is the lower triangular matrix and the other is an upper triangular matrix, knowing very well that this particular system, the lower triangular system, is easy to solve, and an upper triangular system is also easy to solve. So we want to, instead of going through the full square matrix that is neither lower nor upper, we want to split it into two, a lower triangular and an upper triangular, and then use the two matrices to solve two different systems that are lower triangular and upper triangular, and in the end get the solution to the original problem that we have been given. So this is the whole idea behind LU decomposition. We are trying to decompose the matrix into two parts. One is a lower triangular and one is an upper triangular, or the other is an upper triangular. And the methods that we are going to consider are the Doolittle, the Kraut, and the Kolesky. These methods follow the same set of steps. The only difference is that some of them can solve some particular problems, and others cannot probably solve some specific problems. And they all have different way of the decomposition. So they follow the same step, the same general step, but the way of decomposing the matrix into lower and upper triangular are what differs. So eventually we will come through the same set of solution procedure after the decomposition is done. So how is the decomposition? What is the general steps? The general steps of the LU decomposition, as I said earlier, we are trying to solve a system A. We are solving a system AX is equal to B. So we try to set the A to two matrices, a lower triangular matrix and an upper triangular matrix, such that A is equal to L times U. So you are setting the matrix such that A is equal to L times U. And then in place of A, we put our L times U. So you see this particular system, this one, can be written this way. But from our understanding of solving system of linear equations, we cannot solve this particular system directly where L is a matrix, U is a matrix, X is a vector, and B is a vector. All we know is that there must be one coefficient matrix, then the vector of unknowns, and the right-hand side values. So carefully, if I have LU times vector X is equal to B, then it will be difficult to solve, because this is a matrix, this is a matrix, this is a vector, and this is a vector. So what we need is that we need a case where we have only one coefficient matrix and one unknown vector and one right-hand side vector. So what you do is you set this side to be equal to a certain unknown vector. So we're going to have let U times the X be equal to a certain Y, where the size of Y is equal to the size of what? X. So, or the length of Y is equal to the length of X. So you choose any arbitrary vector, you choose any vector, such any unknown vector whose size is the same as the size of X, and set Ux to be equal to that. You see that this is a system that we cannot solve because we don't know X and we don't know Y. The only thing we know at that stage after the decomposition is U. So you can't solve it. But when we substitute the Y there, we are going to have Ly is equal to B. We know the matrix L, we know the vector B, and we can find the vector Y. So when we get the values of vector Y, then we go back into this particular equation and then substitute the Y there. Immediately you substitute Y, then now you know U, you know Y, then you can find the X that we are asked, we are to look for. So this is the basic steps of the LU decomposition. Use a certain procedure to decompose the matrix A into two parts, L times U. Then, in place of A, put the L times U. So we have L times U. We have L times U is X is equal to B. Set the UX part to be equal to a certain unknown vector that has the same size or length as X. And then, when the substitution is done, then you are going to solve the system Ly is equal to B. We know L, we know B, we can find our Y. And so you find the Y. And when you get the Y, we come back and put the Y in this particular equation, where at that stage, we will know Y, we will know U, and we can find our X. So this is the basic steps in the LU decomposition. So using LU decomposition, so you let Ux be equal to Y, a vector of the same length as X, and then solve for Y in Ly is equal to B. Use Y to find X in the Ux is equal to Y, because at that stage we will know Y. So we come and put the values of Y here, and we solve for the values of X that we are looking for. So you see, you are going to solve a lower triangular problem is equal to a certain right-hand side, and that system will look like this one. It will look like this, my system here. It will look like this one, system number one, because you have a lower triangular times an unknown vector X is equal to a right-hand side, and it can easily be solved. And then when that is done, you come and put the values of Y over here, and you are going to have a system that looks like this one, this particular one, this particular system, system number 2. And that it will also be easy to solve, because this one also has what? An upper triangular coefficient matrix. And so when this is solved, you get your results that we're looking for. So that is the whole idea behind LU decomposition. First of all, use any of the three methods that are described up there to decompose the matrix into two, the product of two matrices such that one is a lower triangular and the other is an upper triangular. Then you solve the Ly, a certain new vector y, solve Ly is equal to b, and then use the y to solve ux is equal to y and get the values of ux as we are looking for. So let's start with the Doolittle, which will be for this particular video or this particular lecture. So the Doolittle decomposition, and then we continue on with the solution using the Doolittle decomposition method. So now, the only thing that we're going to discuss now is how to decompose the matrix into two using an approach described by Doolittle. So we are going to just learn how to decompose the matrix A into two parts, L and U, such that using the Doolittle approach. And this, as you see on your screen, is how Doolittle does the decomposition. Let me use a smaller matrix to explain. This matrix, I have A11, A12, A13, A21, A22, A23, A31, A32, and A33. So this is a 3 by 3 case, and the lower triangular, I'm using different notation. According to Doolittle, the decomposition must be, let me call this L1, 1, then 0, L2, L3, and then 1. Then the upper triangular will look like this: U1, U2, U3, 0, U4, U5, 0, 0, U6. So this is the Doolittle decomposition. It puts 1, 1, 1 on the diagonal of the lower triangular, and then all entries below the lower triangular are 0 on zeros or non-zeros, and all above the ones are strictly 0 because it has to be L, the lower triangular, and this is the U. So what you do is that in this first method of the Doolittle, all that you can do, as anyone who has learned matrix linear algebra, matrix multiplication, you would agree with me that we can multiply the L and the U, multiply this L and U, and whatever you get is equated to the matrix given to you. Then you find the values of L's and the values of the small L's and the small U's, and then you use them to just proceed. By finding L1, L2, L3, U1 up to U6, you will get both the L matrix and the U matrix. Then you go to the previous discussion that I gave, the general discussion, and then proceed to solve the problem. So let's see how the multiplication can be done. Matrix multiplication, everybody is clear with that. Row 1 times column 1 will give me U1. Row 1 times column 2 will give me U2. Row 1 times column 3 will give me U3. So that is U3. Then row 2 times column 1 will give me L1 U1. Row 2 times column 2 will give me L1 U2 plus U4. And then 2 times column 3 will give me L1 U3 plus U5. And then we go to row 3. Row 3 times column 1 is L2. Then row 3 times column 2 is L2 U2 plus L3. And finally, this times that will give us L2 plus L3 U5 plus U6. So you see, this two matrices, this matrix and that matrix are equal. So what do we say? U1 is equal to A11. U2 is equal to A12. U3 is equal to A13. Then this particular one is equal to this one. By that time, we will know U1, so you can find L1. Then you come to this guy is equal to that guy. By that time, we know U1, so you can find L2. Then you come, this guy is equal to this one. And by this time, you will know L1 and U2. L1 from here and U2 from there, so you can find U4. Then from there, we go to this and that are equated together. At that time, we have L1 and we have U3, and so we can find that time we'll have L1 from you and then U3 from you, L1 coming from here and U3 coming from here, so we can find U5. Then we get to this guy is equal to this guy. At this stage, we would have U4 already. We have U2 already. We have L2 already, and we can find L3. And when we get the L3, all of them, we'll have L2, U3, L3, U5, and then we can find U6 from here. So after getting all the values of the entries of the matrices on the right, you go back and write your L explicitly. Then you write your U explicitly. Then you start. So when you have, then you start L times U. Then you start your L times U times X is equal to B. So we let go to U, X is equal to a certain Y. Then we solve Ly is equal to B. Solve this one first after you've gotten your L and U. After that, you come and put the Y into the Ls is equal to 1 and solve for X. This will solve for Y and then we solve for X. So this is the decomposition method described as Doolittle. The Doolittle decomposition. So let me take a simple example and then we'll use it for the Doolittle decomposition. This example is what I'm taking, and I'm going to to solve the system. First of all, you need to put the equation into this matrix notation where you get the coefficient matrix. You get the coefficient matrix and then use the coefficient matrix, decompose the coefficient matrix, and then you find the decomposed form L and U and use that to find your answers. So let's see, for the coefficient matrix, everyone here agrees with me that the coefficient matrix is going to be, or let me put the system into the, so the system in matrix form is going to give us 3, 5, 2, 0, 8, 2, then 6, 2, 8 times x1, x2, x3 is equal to 8 minus 7, 26. So we know our A, which this is our A. This is our A, this is our X, and this is our B. So if we have to decompose a matrix, then it is this matrix that we need to decompose. So I'm going to just say that it means that we're going to have A, which is 3, 5, 2, 0, 8, 2, 6, 2, 8, to be equal to the 2, 1, 0, 0, L1, 1, 0, L2, L3, 1 times U1, U2, 3, 0, U4, U5, 0, 0, U6. So this is what we have. And according to the multiplication we have up there, with this, when we multiply these guys, we are going to get U1, U2, and U3. Then we have L1, U1, then L1, U2 plus U4, then L1, U3 plus U5, then L2, U1, then L2, U2 plus L3, U4 plus L2, U3 plus L3, U5 plus U6. So this is the new. So we equate, and straight away we can just say that this implies that U1 is equal to 3, U2 is equal to 5. This guy is equal to this guy. This guy is equal to that guy. This guy is equal to this guy. So then U3 is equal to 2. Having these initial values for free, we can just go ahead to solve for the other values. So let me come to this place and get L1 U1 is equal to the corresponding term there is 0. So 0. Now we know U1 to be 3, so it implies L1 is equal to 0. Then I go to this guy as my next, which is L2 U1 is equal to the entry there is 6. But I know U1 to be 3, so it implies that my L2 is going to give me 6 divided by 3, which is 2. So I can proceed by equating. Now I move to this term and get it as L1 U2 plus U4 is equal to 8. This, I know my L1 is 0, so it means the whole of this will go to 0, and that implies that U4 is equal to 8. And we proceed in that same manner to find the values of all the other values, all the L values, and all the U values. So we can go to this particular term now, and that is going to give us L1 U3 plus U5 equal to, what is the value there? 2. And this implies, because L1 is 0, it implies that U5 rather, U5 is equal to 2. So then next is this particular term here. So I have L2 U2 plus L3 U4 is equal to, the entry there is 2. But what do I have to my credit? I have L2, which is 2, so 2, I have U2, which is 5, plus I have U4, which is 8, so 8L3 is equal to 2. So this is 10. Going to that place gives me negative 8 divided by 8, and my L3 is negative 1. Then finally, I have L2 U3. I'm using this guy now, plus L3 U5 plus U6, and is equal to, according to the value there, is 8. When you substitute all of them in solve, you get U6 to be equal to 6. So from that, we can write our matrix. In place of L1, you put the value of L1 there, which is 0. In place of L2, you put the value of L2 there, which is 2. In place of L3, you put the value of L3 there, which is 1. And so we are going to have, therefore, our L, therefore the L matrix is going to be 1, 1, 1, 0, 0, 0. And what is L1? L1 is 0, L2 is 2, and then L3 is minus 1. Then what is my U? U is given by U1 is 3, U2 is 5, U3 is 2, and then this is 0. U4, we found U4 to be 8, then U5 is 2, 0, 0, and U6 is 6. Like this. So now that we have our L and U, we can now solve the system by using the steps that I described earlier. So we have our A, X is equal to B is what we are solving, but we know LU times X is equal to B. We are saying that let UX be equal to a certain Y. In this case, Y is going to be Y1, Y2, Y3, because X is X1, X2, X3. We said that Y must be of the same size as X. And so we solve now our lower matrix form Ly is equal to B. So let's write Ly is equal to B. Ly is equal to B can be written as 1, 0, 0, 0, 1, 0, 2 minus 1, 1 times Y is Y1, Y2, Y3 is equal to, what is this? The values of B. B is 8 minus 7, 26. This is what we have. You see, this is just like the first system I solved in my intro. So it is a lower triangular matrix, and we are going to solve it easily. Fortunately, this one is much more easier. This is equal to 8. When and then we get Y2 is equal to minus 7. And then we have 2Y1 minus Y2 plus Y3 is equal to 26. So clearly, we have what? Y1 is equal to 8, Y2 is equal to minus 7, and so we have 2 into 8 minus negative 7 plus Y3 is equal to 26. So this gives us 16 plus 7, which is 23. Take the 23 there, and that will give us the value of our Y3, and that gives us Y3 is equal to 3. So you see the vector of Y's, Y1, Y2, Y3, is now known to be 8 minus 7 and 3. So now that we know the vector Y, we can now go back to this system this particular system, we go to the system and solve it. Because now we know y, when we put the value of y here and we put the u matrix, we can now solve for the x that is actually the variables we are looking for from our system on the left side of the screen. So let's go for the matrix. So now we are solving ux is equal to y. And what is my u? My u is 352,082. So I have 352,082,006. And that's times y1, y2, y3. Oh, sorry. Times x1, x2, x3. Times x1, x2, x3 is actually supposed to give us y1, y2, y3. But we know that to be 8 minus 7, 3. So writing the system into the component form, what do we get? We get 3x1 plus 5x2 plus 2x3 is equal to x3 is equal to 8. Then we're going to have 8x2 plus 2x3 is equal to minus 7. And then 6x3 is equal to 3. So you see, we have another very easy system that we are going to solve. And with this particular system, we solve for our x3. So x3 is equal to 3 on 6, which is 1 on 2. Then we have 8. We put that into equation 2 and get 8x2 plus 2 into 1 over 2 minus 7. This gives us 8x2 plus 1 is equal to minus 7. So solving that, we get our x2 to be equal to, I think, negative 1. Also, when this goes there, you get negative 8. When you send this guy across, you get negative 8 divided by 8, so negative 1. Okay. And then finally, we substitute all that into our equation 1. So 3x1 plus 5 into negative 1 plus 2 into half is equal to 8. So this is 3x1 minus 5 minus 5 plus 1 is equal to 8. And what is that? It gives us negative 4. The constants here gives us negative 4, and it goes there to be positive 4. So we have 3x1 is equal to 12, which implies that our x1 is equal to 4. So within the short one, we can have our x1, x2, x3 being given by 4 minus 1 and then what? So this is the Doolittle decomposition plus the general steps of solving the system using the LU decomposition. So first of all, we went through the steps of finding the L and the U using the Doolittle decomposition, which sets the lower triangular to be to have a diagonal entry of 111. Then the 3 entries down there, if it is a 3 by 3 matrix, then the 3 entries down there is L1, L2, L3. You can use any notation you like. ABC is okay. Then the upper triangular must be an upper triangular that all the entries below the diagonal are zeros, but the diagonal and above are other entries. But remember, the lower triangular has strict 111 entries on the diagonal. So that is our LU decomposition using the Doolittle method. So with this one, we are going to now apply in other systems. We can use the same thing in other systems to solve it. So that is the LU decomposition. These are the steps of the steps is what I have described. And the next method is the same Doolittle, but I'm calling it approach number 2. Approach 2. Or as you can see in the approach on your left side, I call it method 2. Not necessarily a method, but approach 2. So the approach 2, what do we know? From my Gaussian elimination video, we have learned how to find the upper triangular matrix using Gaussian elimination. So we're going to use the Gaussian elimination to get the upper triangular matrix of the Doolittle. Remember that we are looking for both the lower and the upper triangular. And in course of finding the upper triangular, you will see the beauty of the use of Gaussian factors and how important the Gaussian factors are in relation to this Doolittle decomposition. So once the decomposition is done, I know that you can come back to the actual steps to finish it through the same procedure. So I'm going to do Gaussian elimination to this matrix that I have. So the system is 3, 5, 2, then 0, 8, 0, 8, 2, then 6, 2, 8. This is the matrix. By Gaussian elimination, we can say that this is equivalent to my pivot row is 3, 5, 2. So to eliminate the second row, what are we going to do? We're going to do row 2 is equal to row 2 minus my Gaussian factor here is what? 0 divided by 3. So it is 0, row 1. So I need that Gaussian factor 0. So when I do this, it is going to give me the same as the row 2, which is this and that. Then the row 3, how do we do the row 3? It is going to be row 3 is equal to row 3 minus, what is the Gaussian factor there? 6. The Gaussian factor is going to be 6 divided by 3, and that will give me 2. 2, row 1. And so when I do that elimination, what am I going to have? 6, 2, 8 is by row 2. 2 times row 1 is going to give me 6, 10, 4. So subtract, and that will give me 0, negative 8, 4. And so 0, negative 8, 4. Then the next stage is equivalent to, now my pivot is the positive 8 here. My pivot is this guy, this positive 8. So I have 3, 5, 2, 0, 8, 2. And so sorry, the pivot is 8, and I need the Gaussian factor to eliminate that one. So row 3 is going to be the old row 3 minus, what is the Gaussian factor now? Negative 8 divided by 8, and that is negative 1. Row 2. So negative 1, row 2. And so when I do that, I'm going to have I'm going to have it come out as 0, -8, 4. -1 times 2 will give me 0, -8, -2. Subtract, and this goes to 0, and this goes to 6. So 0, 0, 6, and so we get 0, 0, 6. You see, if you look at this matrix that we have here, it is the same as the upper triangular that we got from the previous session. It's upper triangular. Look at that. It is the same as that upper triangular. This one is upper triangular. The 352082006 is the same as the upper triangular we are getting from the Gaussian elimination without row swapping. So it has to be without row swapping. So my upper triangular is going to be 352082006. This is my upper triangular. And let me write the lower triangular. The lower triangular, according to what we know, we already know that with the Doolittle, the diagonals are 1, 1. Then the upper part of the diagonal are all 0, 0. And so the only thing we are left with are this place, that place, and that place. These are the three things that we are left with to get our Doolittle, the lower triangular. Look at something. When we were here in the Gaussian elimination procedure, when we wanted to change this particular number, this number to go to 0. I just look at it as if it is not 0. When we wanted to change this number to go to 0, what was the Gaussian factor we used over there? The Gaussian factor is this 0 that I have shaded over here. And that is the number that sits there. When we got to, and that is the number that sits here. When we got to this side, this particular side, when we got here, when we got to this side, when we got here, so it means that when we wanted to change this +6 to go to 0, what is the Gaussian factor we use there? The Gaussian factor we use there is the tick 2 that you see over here, and that is the number that should sit there. This 2. And then finally, I know you can predict what is going to be over here. And that is the number we use to send this particular guy to go to 0. The Gaussian factor we use over there. That is this particular place going to 0. We use this Gaussian factor. That is the reason why I didn't write it as rho 3 plus rho 2. But I made sure that my Gaussian factor is explicitly written. And that Gaussian factor is what is going to sit here as -1. Look at this lower triangular matrix and compare it to the one we had from the previous session, which is this one, this particular guy, or that guy. This particular lower triangle, 1, 0, 0, 0, 1, 0, 2, -1, 1. It's the same thing as this lower triangular we have 1, 0, 0, 0, 1, 0, 2, -1, 0. This is the reason why I told you in my slide or my video for Gaussian elimination that the other way of doing elimination procedure will not help, but you need to understand the use of Gaussian factors because the Gaussian factors are necessary in other mathematical procedures or there are other mathematical methods. And one of such methods is this. If we want to go by the second approach, where you are going to do Gaussian elimination, and use the Gaussian elimination to get your upper triangular as well as the lower triangular. Then you need the Gaussian factors. You need the Gaussian factors to be able to find this lower triangular. And now that we have our lower triangular and upper triangular, everything follows like the previous case. You solve Ly is equal to B. When we get the values of y, then we solve what ux is equal to y. This is the Doolittle decomposition method for solving system of linear equations. I will pause here for this, and in our next video, we will discuss the crowd decomposition. So the second method can be put as this, as you see on your left side. Use Gaussian elimination to get UD, the upper triangular of A. Keep all the Gaussian factors used in step 1 above. Then the below diagonal entries of LD, or the lower triangular, are simply the Gaussian factors used at those stages or used at that stage. And that is how we're going to get our lower triangular and upper triangular. So the rest of the steps follows us in the previous session, or the previous approach of finding L and U, as we discussed earlier. Thank you very much, and see you in the next video for crowd decomposition.